data mining, and we were looking at this pack to do with assessment of this ROC curves and cross-validation. And let me just walk you through this. So we want to have a way of evaluating the performance of our data mining approach. And one of the issues that comes up is we want to be sensitive to how the model generalizes. To do that, there's this notion I think we briefly talked about last time of separating your data set in basically a training and testing set. Sometimes there's also a third validation set, and basically parameterizing your model on the training set, seeing how well it does on the test set. There's this notion of doing this in what's called cross-validated fashion, where you essentially make these splits many different ways with your data. Like you, for instance, you would, if you have all your data set here, you would leave, say, one thing out or a few things out in run one. Then you would put them back in, and you would leave a different subset in run two and run three, and then you would average all of these things together. Now, when you look at the accuracy of your prediction, there's a whole variety of statistics that you can compute. I think the way to think about this is you have the reality of what you're doing. Say you're trying to predict if it's a plane or if it's a bird. And then you have your prediction, plane or bird. Obviously, if they agree, it's a true positive. And if you, well, if you're predicting a plane, it's a true positive. And if you're predicting bird, it would be true negative. And then there's the disagreements where you're saying your prediction is calling out a, say it's a plane, but it's really a bird. And so actually, I think I got that backwards, but I think you get the idea. And there's a variety of statistics that people use for this. They take these four numbers and they can compute accuracy, sensitivity, specificity, true positive rate, false positive rate, and so forth. I find all these statistics a little, sometimes a little bewildering to look at. And I think one way of thinking about it is you can think about the true positives plus false negatives as the set of all things that are real. That's all the known real objects, right? And you can ask what fraction of your true positives is that of the sort of real objects. And then you can sort of, and that gives you your sensitivity. How many things are you finding of the real things, okay? And then another useful metric is sort of your error rate. And I think often you like to think about sort of the number of false positives you're getting versus the size of the sort of negatives. And that's, they say, false positives plus true negatives. And there's a bewildering array of ways of putting these numbers together, and we'll talk about them. Another useful thing is to think about not of the real things that are say the real planes, but of all the things you're saying, you're calling out as positive, what fraction of those things are in fact positive? And that's often called the true positive rate. And that's true positive over, see, it's a slightly different denominator here, TP plus FP. Those are all the things that you're calling out as positive, whether they're true or false, okay? So just notice the difference between the true positive rate and sensitivity. And then for regression, as you know, as for continuous value problems, as opposed to classification problems, we often look at sum of squares errors. That would be a very good way of looking at that. And often we summarize the results of something in something called a receiver operator characteristic curve. I think that's the term, or ROC curve for short. And we try to think about, as we change, say, the threshold in our prediction, the amount of positives that we'll emit increases, but the number of false positives will also kind of increase. And so we kind of can kind of graph kind of the overall coverage of the known positives versus some form of error rate, which is the false positive. And there's a variety of, depending on the exact type of graph you're going to look at, you can put slightly different things on these axes. But the basic idea is there's one axis that's related to kind of the coverage of your positives and one axis related to your error rate. And as you change your threshold, you're going to get more and more coverage, but you're obviously going to get more and more error rate. And for a classification problem that's kind of equi-mixed between positive and negatives, you kind of expect a kind of random classifier to be on this dotted line. And therefore, you know, if you want to evaluate your classifier, often what you do is you kind of look at the amount of area under this curve relative to a random one. So the area under the curve describes how well your classifier does for a variety of different settings, and that's compared to a random classifier, okay, which is sort of at 50%. So you'll kind of look at the total amount of blue area relative to this. Now, you know, I sort of alluded to this issue too when we talked about splitting up the data between test set and training set. We often think a lot about sort of overfitting or over-parameterizing our model. And this is just a little illustration. You've probably all seen this type of illustration before for kind of how a model generalizes and what overgeneralization is. And so here, we're trying to fit a curve. This is a regression problem through these points. And so we can pick progressively more complicated curve so that we can pick. We could pick, say, a 1-degree polynomial, which is a line, something like that. Then we can pick a 2-degree polynomial, which, you know, has a little bit of curve. We could pick a 3-degree polynomial, and then 4-degree, 5-degree, and so forth. And the idea sort of is that as we make our model progressively more complicated, we can fit the curve better, okay? But what tends to happen is if we allow more parameters in our model than there are really data points to refine against, our model will overfit the data. And it will essentially memorize the data, but really have no generalization potential. And that's what you would have, say, with having a 10-degree polynomial or a 15-degree polynomial. And you can just kind of see from the curve, it really seems, even though it's fitting through all the points, it doesn't kind of look like it's really getting the kind of overall sense of the curve. And so this is the type of thing that we want to avoid. And this is called overfitting. And we see this by evaluating the performance on the testing set. And often what you can do here is you can graph your model complexity, which in this particular case is the order of the polynomial, versus your error. And so you can see that obviously, and you can do that both for the training set and for the testing set. And so you can sort of see that as you increase the model complexity, you know, it does better, you know, particularly when you go from 2 to 3. But then you can start to see actually there's a divergence between the training set and the testing set. And so here you can see down here at the 10th degree polynomial, you're memorizing the training set, but actually on the test set, you're doing terribly. And this is kind of a quantitative illustration of this notion of overfitting. I think a related notion to overfitting, but it's not quite the same thing, is if you have many features in a data set, you know, you sort of, you have a certain number of points, but you have a progressively large number of features. As you increase the number of features, you might think, well, you know more about the data points, you should be doing better, but you actually tend to do worse. And this is related to a different issue, and this is the kind of curse of what's called the curse of dimensionality. And the idea is that the kind of space that you're looking at, if you think of each of these features, remember, is kind of like an axis in a high dimensional space, the space dimension grows really, really large that you're sort of looking at relative to the number of points, and sort of the volume of the space relative to the amount of points increases quite dramatically. And that's another particular reason to avoid adding in things. And actually, I should say, we didn't talk about it so much in this class, but sort of related to that, there's also this third notion of multiple testing. And if you test too many times, a lot of times you can come up with spurious results. And that's a kind of, they're not the same thing, but they're all kind of related to each other and so forth. Now, I wanted to just sort of explain the notion of sensitivity and specificity and how you sometimes kind of get strange things happening as the size of your positive and negative set change. You know, and a lot of these curves are kind of intuitive when your positive and negative set are sort of equal size, but they become a little bit unintuitive when the sets are very small. So let's look here. Here's an ROC. So here's an ROC curve, and you've got 1 minus specificity, which remembers the error rate, and then you have some measure of sensitivity, okay? And you have a bunch of things you're looking at here. The size of the circle kind of represents the strength of your prediction, you know, you're saying, and then there's sort of two groups, the sort of lighter group here and then the darker group. And so you can kind of see as you threshold your predictor, you know, if you threshold it really, really harshly, you'll get, sort of great accuracy. You'll not get many things wrong, but you'll only get some of the things in this side. But as you progressively threshold in a weaker way, these types of things will crop in. You know, and this sort of makes sense. That's your normal ROC curve. But now we can think of a situation like, well, what would happen if the data set became very unbalanced? So let's actually use a specific example on this ROC curve here. Let's say that we're thresholding a particular value, and we find that we can get all 5 of these black points here, which are true positives, and there's 25. So we get a sort of sensitivity of about 20%. And we can look at our specificity too, which is the number of things that we get wrong, which is 2 here of 25. That's 8%. And then we can also compute this, like I said, this positive predictive value, which is the number of things we get right, which is 5, relative to the total number of things for which we are giving out a positive prediction, and that's 7, okay? So we'll get 71%. Okay, so now just look at these numbers. So we get a sensitivity here. We get 5 out of 25 right, and then 2 out of 25 wrong, and then we get our positive predictive value. Now, look at what happens when our negatives become much larger than our positives. Okay, and I think a good example of this is the, you might say, like the breast cancer detection problem or the terrorist screening problem. This is a type of situation where you think about this sort of, you have the metal detector and you're trying to find the terrorist. You know, most of the people going through that metal detector are not terrorists. It's a very small number of terrorists. And so you can have a situation where you can have a very good predictor, but most of the predictions are going to be false positives. And that's what I'm going to show you here. So now we imagine we have a data set that looks like this. We still get our 5 positives correctly over the 25 real ones. We get a sensitivity of 20%. But now what's kind of interesting here is since our negative set has increased so dramatically, our specificity, our error rate is still about the same, right? We're emitting the same number of false positives relative to the number of true negatives at a pretty constant rate of 8%. But notice how our positive predictive value has fallen. So that means that now the majority of the things that we're emitting are actually false positives, right? So the majority of things that is emitted by the predictor are wrong, and it seems that our predictor is doing much worse. Its positive predictive value is only a third, okay? Now, from a ROC curve standpoint, it's actually doing the same, but it's kind of in a use scenario. You have this predictor, and only now a third of the time when the light goes off is it accurately, say, finding a terrorist. So now what we can see here too, and let me see if I can sort of walk through this a little bit. This is where we know the previous situations where we kind of knew the positive set and the negative set really well. But imagine we didn't know their full extent. You know what I'm saying? We didn't really know exactly how many things were positive and exactly how many things were negative. And you might say, well, how does that situation arise? Well, often you have a situation like this in, say, a genomic prediction where you're predicting something. You have a set of the genome you're looking at, and you say get 5 things right on that set, and you get all these things wrong, and you know that other thing is much bigger, maybe in the set you're looking at, but you don't know how it relates to the entire scale of the thing you're looking at. Is the data set, is this a sample that's really accurate between this, or the proportions really accurate between the light shaded and the dark shaded thing, or we don't know the full extent. And so here you can no longer compute a sensitivity and a specificity because you don't really know your true number of true positives, or your positives, nor your negatives, but you can produce a positive predictive value. And because you can say, well, I've emitted 15 positive answers, and you can say, okay, from the 15 positive answers I've emitted, 5 of them are correct. So you can get that number of 33% without knowing the full extent of how many things are truly positive, okay? But now, imagine you're in a situation here where you have a predictor and you're emitting positives, okay? And only a fraction of the positives can you assess and even check. So for instance, in this situation here, if you look at only 6 of the positives now, we can actually assess whether they're right or wrong. And then these remaining positives, we don't know if they're either right or wrong. And this is like I said, a situation you often have when you're looking at say a very big data set like the genome. You might say, well, there's a little region of the genome here, and I can assess if these 2 things are positive in the genome, and I can see that these 4 things are wrong. And so on the thing I've looked at, I get a positive predictive value of 1/3, but I don't know if I look at the entire space upon which I want to predict. I don't know the answer for all the other things, and most importantly, you don't know if these proportions of the positives and negatives are reflected in this missing space. And so that's a question of, is this estimate now of 1/3 an accurate estimate for these remaining points? And then, of course, there's the final situation here, which kind of looks comical, but unfortunately is fairly accurate. You have a predictor that's emitting positives, okay? And you don't really, how should I say, you don't even look at how well it does on negatives. If you just say, oh, it predicts, 2 of the things it predicts I can validate are positive, and then it predicts all these other things, and I can't really validate them. And this is the kind of situation, I kind of ironically, what happens in a lot of experimental settings where you'll have something that you'll, some sort of predictor, and you'll validate, say, a small number of the things, like say you validate 5 of the predictions, and they're all right, or something like that. But then it's making many, many more predictions. And you don't know if they're right or wrong. It's just making many more predictions. And so this is kind of the situation you're in. Now notice here, you can no longer produce a positive predictive value because you don't really know how many of those positives that it's emitting are potentially false positives. You just know that you've tried a few things, you've assessed them for positivity, and they're right. Now you might be thinking, well, this is a little comical and so forth, but this is actually fairly typical for the type of assessment sometimes that people have for a predictor in a real world context, because of course, knowing the gold standard truth, which is what's shown by these boxes, is of course very hard. Okay, so with that, I'm going